So a lot of the chemical properties of elements in the periodic table are actually predictable. We can easily determine them because of their number of valence electrons. The number of valence electrons for the main group elements can easily be determined by simply looking at the element's group number. So for example, the alkali metals are in group 1. So all these elements in group 1 will have one valence electron. So the number of valence electron basically matches the element's group number. So group 2 elements will have 2 valence electrons. Group 3 elements will have 3 valence electrons. Group 8 elements will have 8 valence electrons. And so the reason why the elements in the same column have same properties because they have the same number of valence electrons. Group 1a elements are known as the alkali metals, and alkali metals have the same number of valence electron, which is 1. So they have one single valence electron. And these alkali metals are known to be the most reactive metals in the periodic table. Group 7a elements are known as the halogens, and they have 7 valence electrons. These halogens are considered the most reactive nonmetals in the periodic table. The group 8a elements are known as the noble gases, and the noble gases have 8 valence electrons, and they are considered the most stable element in the periodic table. One exception here is helium. Helium only has 2 electrons, and those 2 electrons are considered valence electrons because by definition, valence electrons are the electrons in the outermost shell that are involved in chemical bonding. And so that's one of the main reasons why these elements are so unreactive, because of the fact that they have a completely filled subshell or sublevel. So the next concept that I want to talk about here is the trends in the periodic table. So there are 4 different trends. There's a trend in size or radius. So there's atomic radius and ionic radius. There's also a trend in ionization energy, electron affinity, and the last one is metallic character. So the first trend here is the trend in atomic size or atomic radius. So let's define what atomic radius is. So let's say that we have 2 non-bonded atoms here. And these are basically 2 atoms of the same element, right? How do we define the atomic radius? Well, this dot right here is basically the nucleus. So this is the first nucleus, this is the second nucleus for the second atom. And if we take the distance of the 2 nuclei and divide that by 2, that's basically the atomic radius, the radius of the atom. And this is known as the van der Waals radius, the non-bonding atomic radius. So in that case, the radius r is equivalent to 1/2 the distance between the 2 nuclei. What about for 2 atoms that are bonded together? So let's say that we have these 2 atoms right here of the same element, and they have overlapping orbitals. And this is usually observed in nonmetals, 2 nonmetals that are bonded together. So let's say, for example, homonuclear diatomics like hydrogen gas, chlorine gas, fluorine gas. This is what it would look like, right? So we have 2 nuclei right here. And so just like the definition of van der Waals radius, the radius for this would be half the distance between the 2 nuclei. And this is called covalent radius. And the reason why is because you have electrons that are being shared equally by the 2 atoms. So this is bonding atomic radius, also known as covalent radius. And so the radius is also equivalent to half the distance between the 2 nuclei. And covalent radius is generally smaller compared to the van der Waals radius. And the reason why is because of the overlapping orbitals in covalent radius, or in bonding in 2 bonded atoms. So now let's take a look at the trend in the atomic radius. So let's say we have this periodic table shown here, where francium is the element that's on the far left corner in the periodic table. The atomic radius increases from right to left and from top to bottom towards francium. So what that means is that francium is the largest element in the periodic table. So why is it that the atomic size increases from top to bottom in the same column? What is the explanation behind this? So like, for example, if we look at the first group in the periodic table, we have hydrogen, lithium, sodium, potassium, and rubidium. Why is it that hydrogen is smaller than lithium and lithium is smaller than sodium, and so on and so forth? So we can answer this question by simply looking at the principal quantum number, the main energy level n. So when you look at a periodic table, the principal quantum number or the main energy level increases as you move down a column, right? For example, elements in row 1 will have n equals 1. The elements in row 2 will have n equals 2, and so on and so forth. And so the size of the orbitals basically increases as you move down, resulting in the increase in their atomic radius. So for example, 1s is smaller compared to a 2s, and a 2s is smaller compared to a 3s. So that means that sodium contains a 3s orbital, and that 3s orbital makes it larger compared to lithium and hydrogen. So here's a diagram that basically illustrates the difference in the atomic radius between the four elements: hydrogen, lithium, sodium, and potassium. So hydrogen has the first energy level occupied by an electron. Same thing with lithium, the second energy level is occupied, and so on and so forth. So as you move down a column, the atomic radius increases. So the second question here is, why is it that the atomic size increases from right to left in the same row? So again, looking at the periodic table, we have boron, carbon, nitrogen, oxygen, and fluorine, and the atomic radius increases from right to left. So that means that among these 5 elements shown here, boron would be the largest. So why is it that boron is larger than carbon and carbon is larger than nitrogen? In this case, we can't really use the same reasoning that we did earlier regarding the principal quantum number. And the reason why is because boron, carbon, and nitrogen are all in the same row, row number 2. So that means that they have the same principal energy level. So now we're going to have to look at it in a different angle in terms of number of protons. So we know that the interactions between protons and electrons are 100% electrostatic. We have positively charged protons and negatively charged electrons. And so the greater the number of protons, the stronger the interactions are between the protons and the electrons. And so here the number of protons increases as you move to the right. So when you look at boron all the way to fluorine, fluorine has the most protons, and boron here has the least number of protons. And so the electrons in carbon, right? So if we're comparing boron and carbon, the electrons in carbon are experiencing a much greater pull compared to the electrons in boron. So that means that the electrons in carbon are being pulled closer towards the nucleus, towards the center, which results in the shrinking of the atomic radius. So therefore, carbon is smaller compared to boron. You can also look at it in terms of shielding effect. So what that means is that the inner core electrons shield some of the electrostatic interactions between the protons and the electrons in the outermost shell. So here you can see that boron has 5 protons, carbon has 6 protons, and nitrogen has 7 protons. And because nitrogen has greater number of protons, these electrons in the outermost shell are being pulled closer towards the nucleus compared to carbon and boron. And that results in the shrinking of the atomic radius, and therefore nitrogen is smaller compared to carbon, and carbon is smaller compared to boron. Before we move on to the next trend in the periodic table, let's first take a look at the electron configuration of ions. So ions are charged atoms, and there are 2 different types. There's the positively charged cations and the negatively charged anions. So here let's take a look at anions first. So let's compare the electron configuration of chlorine atom versus the electron configuration of a chloride ion. So remember, if you have a negatively charged ion, that means that you have 1 extra electron compared to a neutral atom. So for chlorine, this is the electron configuration. In the periodic table, chlorine is number 17. So that means that it has 17 electrons total. And so the one shown here is the noble gas electron configuration for chlorine. So when you count the total number of electrons distributed here, we have 10 for neon plus 7 total, and that's a total of 17 electrons. So in that case, a chloride ion would have a total of 18 electrons, Cl minus. So all you have to do is add that one extra electron in the 3p sublevel or 3p orbital. So in that case, now we have an electron configuration shown here, which is Ne3s2 3p6. So again, that single electron was added in the 3p orbital. What about for cations? So here we have calcium, neutral calcium versus calcium ion. So a positive 2 charge tells you that you have 2 less electron compared to the number of electrons for the neutral calcium. And so calcium in the periodic table is number 20, so it has 20 electrons. 20 minus 2, 18 electrons. So calcium ion only has 18 electrons compared to the neutral calcium. So shown here is the electron configuration for the neutral calcium atom. So argon followed by 4s2. And so for a calcium 2 plus ion, we just remove 2 electrons from the outermost layer or outermost shell. In this case, the 4s. So we're going to remove the 2 electrons from the 4s. So this becomes 4s0. So the 4s orbital is now empty. So you don't have to write this. This is redundant. So whenever you're writing the electron configuration for a calcium ion, all you have to do is write down argon in brackets. So let's look at a few examples here. So we have a nitride ion, aluminum ion, and a sodium ion. So how do we write the electron configuration for these ions? So nitrogen in the periodic table is number 7. And so that means this nitride ion has 3 extra electrons. So 7 plus 3, a total of 10 electrons for a nitride ion. And so this would be the electron configuration. So you're adding 3 electrons in the 2p, right? So that means we have He in brackets, 2s2, and 2p6. What about for aluminum ion with a positive 3 charge? So positive 3 means that we subtracted 3 electrons from the neutral aluminum. So aluminum, the element aluminum, is number 13. So 13 electrons minus 3 is 10 electrons. So aluminum 3 plus or aluminum ion also has 10 electrons. So that means that it has the same electron configuration as the nitride ion. What about sodium ion, Na plus? So sodium is number 11, so 11 electrons, and then we'll subtract 1 because of the positive 1 charge. And so we have 10 electrons as well. So that means that sodium ion has the same electron configuration as the first 2 here. So atoms or ions with the same electron configuration or the same number of electrons are said to be isoelectronic with one another. So make sure you remember this terminology, isoelectronic. Alright, so let's look at a few more examples here. Write the noble gas electron configuration for the following and determine those that are isoelectronic with each other. So we have magnesium ion, calcium ion, bromide ion, and sulfide ion. So for magnesium ion, magnesium is number 12, so that means it has 12 electrons, and then you subtract 2, so that's a total of 10 electrons. So that means that it is isoelectronic with the noble gas neon, because neon has 10 electrons. For calcium 2 plus, calcium is number 20, so it has 20 electrons, and then you subtract 2 from 20, and we have 18 electrons. And argon, a noble gas, also has 18 electrons. So that means this calcium ion is isoelectronic with the noble gas argon. And the third one here is bromide ion. Bromine is number 35, and so it has 35 electrons, and then we're going to add 1 electron because of the negative charge. So now we have a total of 36 electrons for the bromide ion. And the noble gas krypton also has 36 electrons. And so bromide ion is isoelectronic with krypton. And the last one here is the sulfide ion. Sulfur is number 16. So it has 16 electrons plus 2, a total of 18 electrons. So that means that sulfide ion is also isoelectronic with the noble gas argon. So as you can see here, the calcium ion and the sulfide ion are both isoelectronic with one another. So what we've looked at so far is the electron configuration for main group elements, the group A elements. What about for transition metals or the group B elements? So let's take a look at the electron configuration for iron and iron ion, Fe3+. So for iron in the periodic table is number 26. So that means it has 26 electrons. And the preceding noble gas is argon. And then the rest is 4s2 and 3d6 for a total of 26 electrons. So iron 3+ tells us that this iron ion has 3 less electrons compared to the neutral atom of iron. So how do we subtract 3 electrons from this electron configuration? So again, a positive 3 means that we have 3 less electrons, and so we have to remove the electrons from the outermost shell, which is basically the valence shell. So in this case, in iron, you're going to take the electrons from the valence shell first before taking the rest from the other orbitals, like the 3d orbitals. So in that case, we're going to subtract 2 from the 4s and then the other electron from the 3d. So in that case, the electron configuration for iron 3+ is Ar 3d5. So again, we have to remove the electrons from the outermost shell, which is basically the highest S&P subshell. So another concept that I want to talk about here is the difference between paramagnetism and diamagnetism. So in paramagnetism, atoms or ions containing unpaired electrons are considered paramagnetic, meaning they respond to a magnetic field. So diamagnetic is the complete opposite. The atoms or ions with paired electrons have no response to a magnetic field. So let's look at a few examples here. Let's say silver. Let's say we have a silver atom. The electron configuration for a silver atom looks something like this. So we have krypton, 5s1, 4d10. And the orbital diagram looks something like this. So you have 1 box for the 5s and 5 boxes for the 4d. So all the electrons in the 4d are paired up. In 5s, you only have 1 electron. So you have 1 unpaired electron. So therefore, a silver atom must be paramagnetic. What about for silver ion? Is this also paramagnetic? Well, we have to look at it in terms of orbital diagram again, right? So the orbital diagram for a silver ion would be similar to this one right here, except the 5s would now be empty, right? Because again, a silver plus means that you've removed 1 electron, and you have to remove an electron from the outermost shell, which is basically the valence shell. So you're going to remove 1 electron from here, leaving the 4d completely filled and all paired. So that means that we have a diamagnetic diamagnetic silver ion. So here's another example. We have zinc, and the electron configuration for zinc is shown here. So we have argon 4s2 3d10. So you can already tell that all the electrons in zinc are paired up. And so therefore zinc must be diamagnetic. What about zinc plus, a zinc ion with a positive 1 charge? So this tells us that we've removed 1 electron from the zinc atom, and so you would remove it from the 4s. So once you remove 1 electron from the 4s, then we have 1 unpaired electron. So a zinc ion must be paramagnetic. All right, so let's take a look at a few more examples here. Determine whether the following ions are paramagnetic or diamagnetic. The first one here is aluminum ion, aluminum 3 plus. So the first thing you want to do here is to write the electron configuration and the orbital diagram and see if we have any paired or unpaired electrons. So aluminum 3 plus has 10 electrons, and so the electronic configuration must look something like this. So we have helium 2s2, 2p6. So that means that all the electrons in the 2s and the 2p are paired up. And so in that case, aluminum ion is considered diamagnetic. So it will not respond to a magnetic field. What about the sulfide ion, S2 minus? So sulfide ion has 18 electrons, and the electron configuration is shown here. And as you can see, again, both the 3s and the 3p are completely filled. So that means that all the electrons are paired. In that case, sulfide ion is also considered diamagnetic. And finally, we have iron 3 plus, iron 3 ion, and it has 23 electrons total. The electron configuration is shown here. So you have 4s2, 3d3. So just by looking at the electron configuration, you can already tell that iron 3 ion is going to be paramagnetic. Here's the orbital diagram, and as you can see here, all these 3 electrons in the 3d sublevel are unpaired, and therefore this ion is going to be paramagnetic. So the next periodic trend that I want to cover here is regarding ionic radius. And we know that ionic radius is different from atomic radius. In atomic radius, you have radius of the atoms, whereas in ionic radius, you have radius of an ion. So you have anions versus cations, right? So cations are the positively charged ions, and they tend to be a lot smaller compared to the neutral atoms. And so, for example, if you have sodium and you're comparing that to the sodium ion, so in the sodium ion, you have one less electron. And so when you look at it in terms of the Bohr's model of the atom, so you have the nucleus at the center, and then you have the outermost layer or outermost shell. That outermost shell has one single electron, which is basically the valence electron. And so for the sodium ion, you have one less electron, and that electron in the outermost shell was basically removed. And so in that case, this outer shell right here would become empty, right? And because of that, you have a smaller radius for the sodium ion compared to the sodium atom. So the removal of an electron, the outermost electron, reduces the size of the atom. And so for all positively charged ions, for all cations, the trend in size is actually similar to the trend for atomic radius. So the radius increases from right to left and from top to bottom. So if you're comparing sodium ion and magnesium ion, you have sodium on the left, magnesium on the right. The sodium ion would be larger in ionic radius compared to the magnesium ion. The negatively charged anions, on the other hand, are actually much larger compared to their neutral atoms. And the reason why is because you're adding an extra electron, or these anions have extra electron compared to a neutral atom. So for example, if we're looking at chlorine atom versus a chloride ion would be larger compared to the chlorine atom. And again, you can imagine this in terms of Bohr's model of the atom, where you have the nucleus and then the electrons surrounding the nucleus. So in the chloride ion, you have one electron added to it. And so the addition of electrons weakens this interaction between the positively charged protons and the negatively charged electrons. It weakens the electrostatic interaction. And so the electrons are being pulled less by the protons, causing the size to increase. So anions are larger compared to their neutral atoms. And so the trend is also the same as for cations and neutral atoms. It increases from right to left and from top to bottom. So if we're comparing a nitride ion and an oxide ion, a nitride ion is farther to the left compared to the oxide ion, and therefore larger than the oxide ion. The next periodic trend that I want to cover here is regarding ionization energy. This is basically the energy required to remove an electron from an atom or ion in its gas form. The energy required to remove the first electron in an atom is that atom's first ionization energy. The energy required to remove a second electron would be the second ionization energy, and so on and so forth. The first ionization energy is lower in energy compared to the second ionization energy. Likewise, the second ionization energy is lower in energy compared to the third ionization energy. And so basically, the more electrons you remove from an atom or an ion, the greater the amount of energy required. So here's a few examples. So let's say we have a sodium atom in its gas form, right? So if you remove an electron from a neutral atom of sodium, it would require 496 kilojoules of energy per mole. And if you were to remove another electron from this ion, sodium ion, a second electron, that would require 4,560 kilojoules per mole. So that's almost tenfold difference. So the third ionization energy is greater than the second ionization energy, and the second ionization energy is greater than the first ionization energy. So the general trend in the first ionization energy is shown here. So if you have a periodic table, the first ionization energy increases from bottom to top and from left to right in the periodic table. So the noble gases on the far right hand corner in the periodic table, those elements have the highest ionization energies. So let's take a look at a few examples here. Which one has the higher first ionization energy? So the first one here is aluminum compared with sulfur. So in the periodic table, both aluminum and sulfur are on the third row, and sulfur is on the right-hand side of aluminum, and so sulfur has the higher first ionization energy. The second one here is arsenic, and we're comparing it with antimony, Sb, right? So As versus Sb. In the periodic table, arsenic is right above antimony, and so arsenic would have a higher ionization energy than antimony. The third one here is nitrogen versus silicon. We know that nitrogen is right above phosphorus, and silicon is on the left-hand side of phosphorus, and so nitrogen in this case would have a higher first ionization energy than silicon. And the last one here, we have neon versus chlorine. And so we know that the first ionization energy increases from bottom to top. And we know that fluorine is right above chlorine in the periodic table in group 7A. So fluorine would have a higher first ionization energy compared to chlorine. And then we have the noble gas neon on the right-hand side of fluorine, which has a greater first ionization energy than fluorine. And so therefore, neon has a greater first ionization energy than chlorine. You might want to take note that there are some exceptions in the trend for the first ionization energy. So for example, group 2A elements actually have greater first ionization energy than group 3A elements. So you would expect group 3A elements to have higher first ionization energy compared to the group 2A based on the general trend, right? It increases from left to right. So you would expect group 3A to have higher first ionization energy than group 2A. But in fact, it's the reverse, right? So group 2A will have higher first ionization energy compared to the group 3A elements. So let's take a look at some examples here. We have beryllium. Beryllium has higher first ionization energy than boron. So when you look at the electron configuration for beryllium, it's shown here. So we have helium 2s2. For boron, it's helium 2s2, 2p1. So you have one electron in the p subshell. For regarding the orbital diagram, you have this orbital right here that's completely filled. For boron, you have the 2s orbital completely filled, but then the p orbitals partially filled. So now the question here is which electron is more difficult to remove, or which electron is easier to remove. So here you have one electron in the 2p, and this electron is actually a lot easier to remove because it is unpaired compared to something that's 2s2. So this one requires additional energy to remove this one of the electrons because of the fact that they are paired up. And same thing with group 5a elements versus group 6a elements. You would expect group 6 to have higher first ionization energy compared to the group 5 elements, but when in fact it's actually the reverse. So for example, nitrogen has higher first ionization energy compared to oxygen. When you draw the orbital diagram for nitrogen, you have the 2p sublevel to be completely half filled compared to oxygen's 2p sublevel. It's partially filled, and so it's a lot easier to remove an electron from the partially filled orbitals compared to something that's completely half filled. Another periodic trend that I want to cover here is regarding electron affinity. And electron affinity is different compared to ionization energy, but this is also a type of energy. So electron affinity is the energy change after gaining an electron by an atom or an ion in its gas state. And this is usually negative in value, again, because when you add an electron to an ion or an atom, it stabilizes the atom or ion. And so when it does that, it releases energy. And so electron affinity is negative in value. So that tells you that energy is being released. An example given here is for chlorine, right? So we have chlorine gas, and when you add an electron to the chlorine atom, you get chloride ion in gas form. And this process generates 349 kilojoules per mole. So that means that this process, the addition of electron, produces or releases 349 kilojoules per mole of energy. In terms of electron affinity, most groups don't really exhibit any definite trend in electron affinity, but you do have to remember that in group 1 elements, right, in alkali metals, electron affinity becomes less negative as we move down the column. So that means that the amount of energy that's being released, the amount of energy in kilojoules per mole that's being released, is less as you go down a column. And so if you're looking at lithium versus sodium, lithium would have a higher electron affinity than sodium, meaning the amount of energy that's released by a lithium atom is greater than the amount of energy that's being released by a sodium atom. So again, less energy is being released as you move down a column. The second general trend here is electron affinity generally becomes more negative as we move to the right across a period or row. So what that means is more energy is being released as you move to the right in a specific row. So if we're comparing sodium and magnesium, magnesium would generate or release more energy compared to sodium when electron is added to the atom, the magnesium atom. So there are also exceptions when it comes to electron affinity, and the reason behind this is similar to that for ionization energy. So it has something to do with if you have a completely half-filled orbitals compared to something that's only partially filled orbitals. So if we look at group 2 elements, for example, if you were to draw the orbital diagram for group 2 elements, let's say magnesium. Magnesium has 2 electrons in its 3s orbital. So what that means is magnesium is already pretty stable itself, and adding an electron to it would actually require additional energy. So the group 2A here would actually require additional energy, and so the electron affinity value would actually be greater than 0. It's a positive value because it requires energy to add another electron to it. So let's take a look at a few examples here regarding electron affinity. So we have these elements: lithium, beryllium, boron, all the way to oxygen. And we have the electron configuration already provided here, as well as the orbital diagrams for each element. So when you look at lithium, you can see that there's only one electron in the 2s orbital. And so it would actually stabilize lithium when you add an electron to the 2s, because it makes the 2s completely filled. Remember that a completely filled sublevel, it means that it's stabilized. And so adding an electron here would actually release energy. So that means that electron affinity for lithium would be a negative value. For beryllium, on the other hand, this is already completely filled 2s sublevel or 2s orbital, and so it would actually require additional energy to add another electron here for beryllium. For boron, it would stabilize the 2p sublevel by adding another electron here, so a negative value will be expected for boron's electron affinity. Same thing with carbon, a completely half-filled 2p sublevel is definitely stabilizes an atom. For nitrogen, on the other hand, this is already completely half-filled, so this is already stable. Adding another electron here would actually require some input of energy. And for oxygen, this would also stabilize the 2p by adding another electron here. And so the electron affinity values, this would be negative here for lithium, positive here, negative, negative, positive, and then negative. And these are the values for the electron affinity for each atom shown here. All right, so again, we have a negative value for electron affinity for lithium because it stabilizes the lithium. For nitrogen, this is already stable because it's completely half-filled, and so adding another electron would actually require some energy input. So regarding electron affinity, here's a few things that you might want to remember. A more negative electron affinity means more stabilized. A positive electron affinity indicates that electron is required in order to add an additional electron. And a half-filled sublevel or subshell is more stable than a barely half-filled sublevel. So the last periodic trend that I want to talk about here is regarding metallic character. And this basically describes how metallic an element is in the periodic table. So of course the metals are more metallic in character compared to the non-metals. Let's look at some of the physical and chemical characteristics of metals. They are good conductors of heat and electricity. They are malleable, which means that they can be hammered into shapes. They are ductile, which means that they can be drawn into wires. They are shiny, and they tend to lose electrons. On the other hand, the nonmetals are the complete opposite. So they are poor conductors of heat and electricity. They are dull, they're brittle, they easily break, and they tend to gain electrons. And the trend in the metallic character is shown here. So you have periodic table. The metallic character increases from right to left and from top to bottom towards francium. All right, so this slide right here basically summarizes the all the trends that we looked at. So we looked at ionization energy, atomic radius, ionic radius, and metallic character. And so for ionization energy, it increases from bottom to top and from left to right towards the noble gases. Whereas for atomic radius and metallic character, it increases from right to left and from top to bottom towards francium.